Welcome back to AI.Code.Cast. Ready to dive into another algorithmic challenge.
Absolutely. Always up for a good brain teaser.
Today's problem is called minimum increment to make array unique. It sounds simple at first, but there's a lot to unpack when we start thinking about efficiency.
Yeah, it's a great example of how a seemingly straightforward problem can lead to some really clever optimization techniques.
So let's break it down for our listeners. We get an array of numbers, right? And our goal is to find the absolute smallest number of times we have to increment those numbers so that each one is unique.
Right. Like if you had the array 1, 2, 2, you'd only need one increment because you could just bump that second 2 up to a 3 and you'd be all set.
Okay, I see that. Seems pretty manageable. But I'm guessing it gets trickier when the arrays get bigger and more complex.
Exactly. That's where the real challenge comes in, how to make your solution efficient enough to handle those massive data sets.
Gotcha. So before we get into the fancy algorithms, let's talk about that first instinct a lot of us have, brute force. It might not be the most elegant, but it's a good starting point, right?
Sure, brute force can be helpful for understanding the mechanics of the problem. So in this case, the brute force approach would involve going through the array, number by number. You'd check each number against every other number to see if it's a duplicate.
Okay, so far so good. And if we find a duplicate?
Well, if it's a duplicate, you increment it. And here's the inefficient part. You have to recheck the entire array again. Make sure that the new number you just created is actually unique.
Ah, I see. So it's like a never-ending loop of checking and incrementing until every single number in the array is unique.
Precisely. And you can imagine as the array grows larger, all those repeated checks, it just becomes a computational nightmare.
Yeah, I'm already feeling the inefficiency just thinking about it. What would be the time complexity for something like that?
Oh, this is classic ON2, where then is the length of the array. So as your array gets bigger, the time to solve this problem could grow exponentially, not something you want in a real-world application.
Definitely not ideal.
Yeah.
Okay, so brute force is out. What's a more strategic approach? I feel like maybe sorting the array could be helpful. Like if the numbers are in order, wouldn't it be easier to spot those duplicates?
You're thinking along the right lines. Sorting is actually at the heart of one of the most effective solutions for this problem.
Okay, I'm intrigued. Let's call this the optimized sorted array iteration solution. Walk me through it.
Okay, so let's say our array is 3, 2, 1, 2, 1, 7. The fourth step, like you said, is to sort it.
Okay, so after sorting, we get 1, 1, 2, 2, 3, 7. Now what? Do we start comparing from the very beginning?
Well, the first element is always going to be unique because there's nothing before it, right? So we actually start at the second element.
Ah, makes sense. So in our sorted array, that second element is another one, a duplicate.
Exactly. And since it's a duplicate, we need to increment it to make it unique.
So bump it up to a 2-foot.
You got it. And we keep track of that increment. That's one step towards our final answer. Now we move on to the next element, which is a 2-foot. But we already have a 2, so
We got to increment that one too, right? Make it a 3.
you're catching on quick. Basically, we want to make sure each number is larger than the one before it to ensure uniqueness. And we keep doing this until we've gone through the whole array.
So our final unique array would be 1, 2, 3, 4, 5, 7. And we made a total of 6 increments, which is our answer.
Perfect. You nailed it.
I like it. Pretty straightforward once you see the pattern. But how does this stack up against our brute force approach in terms of efficiency?
Way better. The heavy lifting is done by the sorting. And if we use a good sorting algorithm, that takes ON log n time. The part where we go through an increment is only ON.
Definitely a big improvement over O&M. But what about space complexity? I know sorting can sometimes require a bit of extra memory, right?
That's true. Sorting might require extra space, especially if we can't sort the array in place and have to create a whole new sorted copy. It's something to be aware of. And even though ON log n is generally pretty good, it could still be a bottleneck for massive arrays.
Interesting trade-offs to consider. So sorting gets us a more efficient solution, but it's not always the perfect answer. I'm guessing there are other approaches out there.
Absolutely, there are. In part 2, we're going to look at a solution that uses a frequency map and something called incremental propagation. It's a whole different way of thinking about the problem.
All right, I'm hooked. Listeners, we'll be back with part 2 soon to explore those frequency maps and see how they can help us optimize our code even further. Welcome back to AI.Code.Cast. So last time we left off with a pretty neat solution using sorting to tackle the minimum increment to make array unique problem. But like you said, there's always more than one way to solve a coding challenge.
Right, and sometimes those different approaches can be even more efficient depending on the specific problem.
I like where this is going. So what's this other method you mentioned? Tell me about frequency maps.
Yeah. Frequency maps, they can be super useful, especially when we're dealing with a lot of duplicates in our array.
Okay. Remind me, what exactly are frequency maps again? I feel like I've heard the term before, but I'm a little fuzzy on the details.
No worries. It's basically a way of keeping track of how many times each unique number appears in our array. Think of it like a tally chart or a dictionary where the keys are the numbers and the values are their counts.
Oh, I see. So if RA was 1, 2, 2, 3, 1, our frequency map would have 1 with a count of 2,
Equidip.
2 pit also with a count of 2, and then 3 with a count of 1.
Exactly. It's like creating a histogram of our array, which gives us a clear picture of the distribution of those numbers.
Got it. So we've got this frequency map. How do we actually use it to find the minimum number of increments we need?
That's where things get really interesting. We're going to use a technique called incremental propagation. Basically, we're going to go through our frequency map, starting with the smallest number. Let's say that's 1 in our example.
Okay, so we find 1 in our frequency map, and then what?
If that number 1 appears more than once, meaning we've got duplicates, we need to calculate the excess. That's how many extra ones we have beyond that single one. We need to keep it unique.
So in our example where 1 appears twice, the excess would be 1, right? Because we have one more 1 than we need.
You got it. Now, instead of just incrementing that extra one randomly, we're going to add that excess of 1 to the count for the next number in our frequency map, which in our case would be 2.
Wait, why are we adding it to 2? Wouldn't that mess up our count for how many 2s we actually have?
I know, it seems kind of counterintuitive at first, but this is actually the key to making this approach really efficient. By adding that excess from 1 to the count for 2, we're basically saying, hey, we've got this extra 1 here, so when we get to dealing with the 2s, we might need to do some extra incrementing to make room for it. It's like we're strategically shifting those potential duplicates down the line.
My brain is doing some gymnastics here, but I think I see what you're saying. So
Yeah.
now our count for 2 would be 3, right? It's an original count of 2 plus that extra 1 from the ones.
Exactly, and we just keep doing the same process for each number in our frequency map. If 2 has an excess, we add it to 3, and so on. This propagation ensures that we're always incrementing to the next available slot, so we're minimizing the total number of increments needed.
I'm starting to see the elegance here. We're not just randomly incrementing, we're very carefully moving those duplicates forward to make sure we're using the smallest number of increments possible.
Precisely. It's
Yeah.
all about working smarter, not harder, right?
Right. Okay, let's talk efficiency. What would be the time and space complexity for this frequency map approach?
So the time complexity for this one is O(n) plus m, where n is the length of our original array, and m is the number of unique elements.
Okay. And what about space complexity? I'm guessing the frequency map itself is the main factor there, right?
You got it. The space complexity is OM. The size of our map really just depends on how many unique numbers we have, not the overall length of the array.
So this sounds like a really efficient approach, especially if we have lots of duplicates, which would keep that m value relatively small. But are there any downsides or situations where this might not be the best choice?
Yeah, there's one thing to keep in mind. If our array has a massive range of numbers, like 100,000 to 200,000, our frequency map would need to have entries for all those numbers, even if they only appear once. And that could become a real memory hog.
Right, so it's not a one-size-fits-all solution.
Exactly. Like with any tool, it has its sweet spot. Frequency maps are great when we have a reasonable number of unique elements, but for those arrays with super wide ranges of values, we might need to consider different data structures or algorithms. But before we get into those, there's one more solution I want to show you, and this one uses the principles of something called count sort.
All right, count sort. I'm already intrigued. Listeners, stay tuned for part 3, where we'll break down that solution and see how it compares to our sorting and frequency map approaches.
Welcome back to AI.Code.Cast. We've been on quite a journey with this minimum increment to make array unique problem, haven't we? Explored some really interesting solutions using sorting and frequency maps.
Definitely. And now we've got one more trick up our sleeve. This one draws inspiration from a sorting algorithm called count sort.
Count sort. Okay, now I'm curious. But before we go any further, just to reassure our listeners, we're not actually going to be sorting the array with this solution, are we? Nope. No sorting this time. We're simply going to borrow count sort's clever way of counting elements to make our solution even more efficient.
Right, I like the sound of that. So, spill the beans. How does this count sort inspired approach work?
Okay, let's imagine we have our array, say 4 tier 1, 2, 4. The first thing we want to do is figure out the range of numbers we're working with.
Okay, so in this case, our smallest number is 1 and our largest is 4.
Right, so our range is from 1 to 4.
Got it. So we've established the boundaries of our numerical playground. Now what?
Now we create something called a frequency array.
Frequency array. Okay, and what does that look like?
Well, it's an array that has a slot for each number within our range, from 1 to 4 in our example. And each of those slots is going to keep track of how many times that specific number appears in our original array.
Ah, so it's kind of like a customized frequency map that's perfectly tailored to the exact range of numbers we have in our array.
Oh, exactly. No wasted space. It's super efficient. Then we go through our original array, that 4, 2, 1, 2, 4, and for each number, we increment the count in the corresponding slot in our frequency array.
Okay, I'm following so far. So at the end of that counting process, our frequency array would tell us that 1 appears once, 2 appears twice, 3 doesn't appear at all, and 4 appears twice.
You got it. Now here comes the cool part. We're going to go through this frequency array, and for each slot, we check if the count is greater than 1. If it is, that means we've got duplicates.
Right, and like with the frequency map approach, we need to figure out the excess, how many extra copies of that number we have.
Exactly. So for 2 and 4 in our example, the excess would be 1 for each because they both appear twice. But instead of randomly incrementing, we're going to use that same propagation technique we saw with the frequency map. We add that excess to the count in the next slot of our frequency array.
So the excess of 2 would get added to the count for 3, and the excess of 4 would get added to the count for 5, even though 5 wasn't originally in our array.
Precisely. It's like this clever chain reaction where we just keep passing those excesses forward. And in the end, the total of all those excesses we've accumulated is the minimum number of increments we needed to make the whole array unique.
I really like how this solution leverages the counting mechanism of count sort without actually sorting the array itself. Really smart. But you know me, I gotta ask about efficiency. What's the time and space complexity looking like for this method?
So time complexity for this one is O(n) plus k, where n is the length of our original array, and k is the range of numbers in that array.
Makes sense. And space complexity. I'm betting it's all about that frequency array, right?
Bingo. Space complexity is okay. The size of our frequency array is directly determined by that range of numbers.
So this sounds like a really solid option when the range of those numbers is relatively small compared to the size of the array. But I could imagine it becoming less efficient if that range gets really wide, right?
That's a sharp observation. If our range of numbers, that k value, becomes way bigger than the length of the array, then yeah, our frequency array could start eating up a lot of memory. And in those cases, a frequency map might be a better choice.
Well, this has been an awesome deep dive into the minimum increment to make array unique problem. We've explored 3 really clever solutions, each with its own unique strengths and trade-offs.
Totally agree. We saw how sorting, frequency maps, and even the ideas from count sort can help us optimize our code and make it more efficient.
The big takeaway here, listeners, is that there's rarely a single right way to solve a problem in coding. Understanding the different approaches and their trade-offs is what allows us to pick the best tool for the job.
Absolutely. And sometimes the most efficient solution is also the most elegant one.
Love that.
So next time you're facing a tricky coding challenge, remember to get creative, explore different data structures and algorithms, and most importantly, have fun with it. That's all for this episode of AI.Code.Cast. Thanks for joining us on this deep dive into algorithm optimization, and we'll catch you next time for more coding adventures.